All right. Hello, everyone. Welcome to the section for today. We will be talking about the inverse trigonometric functions. I want you to take a very good look at this page because the basis of everything we're going to be doing with inverse trig, the foundation is based on this three paragraphs. So the first inverse trig function we're going to be looking at is the inverse sine function. And the inverse sine function, it's written as y equal to sine inverse of x. Okay, because I'm not writing in LaTeX, so I had to write it that way. And it has a domain. So remember when we talked about domain are your x values. So this means that x comes from -1 to 1, and it has a range. So essentially when you plug in any x within -1 to 1, you would have the sine inverse of x be in -pi/2 to pi/2. Okay. The one for cosine is just, again, it is cosine inverse, so just at the top, and x is from -1 to 1, and it has, but this case it has a range of 0 to pi. Okay, so this cannot have negative values. So a cosine inverse can never have negative value. That's just what this is saying. It ranges from 0 to pi. And for tangent, we have that tan is equal to tan inverse. I probably should have changed colors for this, but that is okay. And this is valid over the entire real line, -infinity to infinity. And the range in this case is actually open. So remember, open parenthesis as an interval notation means that the end values are not included. Okay. So the difference here is for the end values included, for tangent not included. Okay. So again, this page or whatever information we have on here is extremely important. You need to know the domain of the inverse sine function, the domain of the inverse cosine function, and the domain of the inverse tangent function. Okay, now let's move to seeing what the graphs of these functions look like. So first, let's look at the graph. I think I have all three on the same page, so it wouldn't really make any sense. So this is the one for sine. So this is sine inverse. I already have them written down, so it doesn't really make any sense. So over here, and again, this is all coming from the textbook, so it's nothing new. We have the two graphs. So you have the graph for the sine, so the regular sine x. So you have the graph for the regular sine x, and an inverse function. Again, you looked at inverse function with Julian in I can't remember what section or what chapter, but it's like it's just taking the graph of your regular function and flipping it. So the inputs become the outputs become the input. I don't know if that makes sense, but essentially that's what inverse function does. It just gives you the inverse. It's like flipping along the x equal to or y equal to x axis. And so this is the one for sine inverse, this is the one for cosine inverse, and this is the one for tangent inverse. Okay. Next, we're going to look at an example, but first, let's see how this inverse functions are related to our regular old function, because again, they are the inverses of the regular trig functions that we're familiar with. So this is also very important, this box right here, because it tells you that if you have functions in this interval, okay, and again, this interval is strictly, so now remember that this interval is the range of values for sine, This is the range of value for cosine. This is the range of value for tangent, okay? So if sine of y equal x, then sine inverse of x equal y. So essentially what it's telling us is if, I'm gonna answer this question soon. Let me just use a different, okay, so if I tell you that sine of say pi over 6 is 1/2, then sine inverse of 1/2 is pi over 6. So again, the output for the inverse functions are angles. So output for inverse functions are are angles. So whatever you're putting in to an inverse function, the x of an inverse trig functions are regular good old numbers, but the output must give you angles. And that's just what it's explaining here. If cosine of y is x, then cosine inverse of x was actually y. And the same thing for tan. So for this example, it says given cosine 0.5 is 0.8776, write a relation that involves the inverse function. So it's just like what you have in the box. You have cosine, so now in this case, this would be your y and this would be your x. Then it means that cosine inverse of 0.8776 is approximately 0.5. And that's it. This was just asking you for a relationship between this and the inverse function. Okay. Next, let's look at finding exact values of the expression that involves this inverse trig functions. Okay. So for example, if we have a special input value, and this, so when we say special input value is from like the ones that we are already familiar with, like most of the pi over 6 or pi over 3 or 1 or just those old good old functions. Okay. Now let's look at the following examples. Okay. Part is again, the is just explain, and if you're given as a value, you can find trig function. Okay. So going in reverse, let's take example A now. Going in reverse of what we did in the previous page, here we have that sine inverse. So let sine of negative be equal to say r. Then sine of r is equal to negative. It's just going to what we say. If sin is equal to 1, very careful. It's not always. It's not in the stands. You can have more than one. Remember the idea of reference angles. We can use more than one. We can use more than one. How more than one angles can give you the same final answer. Okay. So now we're trying to find an r that satisfies this. Actually, there's so many values that would satisfy this, again, like I'm saying, but we need r, so we need r to be between negative pi over 2, pi over 2. Okay, so this is very, very important for us to remember that r has to be within the input. Okay, it has to be between the intervals in this. So it has to be between that. Okay. All right, now let's think about it. What angles would give you -1? If you look at your good old regular unit circle, the point where sine is -1, the point where so the point where sine of something is -1 is r equal 3 pi over 2. But again, remember, we're trying to make sure that the angle or whatever we're looking for, but 3 pi over 2 is not in this interval. And so what we have to do now is find a reference angle that puts 3 pi over 2, that is the same as 3 pi over 2, but it's within that interval. And of course, you can do that by probably going counterclockwise, because again, this is 3 pi over 2, so it's this line. So this is 3 pi over 2. And so if we came this way, this would give us -pi over 2. And that is in there. Okay, so again, this is the reason why. That's because, so sine of 3 pi over 2 is the same thing as sine of -pi over 2. So r equal -pi over 2 is our answer, because again, that is in the interval that we are interested in. Okay. Next, let's look at tan. So tangent. Let me just scroll in and change pens here. We're trying to find tan inverse of -1. So we're trying to find tan of, now let's just call it S is equal -1. Again, if you think about your, what's this called again? So we can't necessarily use the unit circle here because this is tangent. Remember, tangent is sine over cosine. And so, but if you look at your unit circle, remember the axis. So A, C, T, S, and it means that, so everyone is positive here, only sine is positive here, only tangent is positive here, and only cosine is positive here. So whatever we're looking for cannot be here. This is also cannot also be here. So it can be here or be here. But then where is -1? -1 is right down here. Okay, remember this is an X value, this is a Y value. So this is -1. Let me just change pens. So remember this is an X value, this is an, okay. So -1 is right here. And now we just need to find that angle that gives us -1 in here. Okay, so that would be in the 4th quadrant. And in that case, that would be the 7 pi over 2. Okay, so S is 7. Oh, sorry, 7 pi over 2, 7 pi over 4. But this is not in -pi over 2, pi over 2. So now we have to use our idea of reference angles to put this to somewhere that is in here. And there, you can do this in multiple ways. You can do, so let me just change a pen for this. Okay, you can do 7 pi over 4 minus 2 pi. That gives you -pi over 4. And that is definitely in what we're looking for. That's in the interval that we seek. So a good answer would be -pi over 4. Okay, I'm sorry that everything feels like it's all over the place. I think I can move this so that it doesn't seem like it's in the, okay, good. And I can also draw a line to separate these two problems. Okay, Now let's add a page and try to solve the remaining two problems. Try to get okay. Problem C of -1 C says C such that it gives us one is easy because if you look at your unit circle, the point where cosine is -1 would so good. Last question inverse. Again, we can of let's try. All right, I'm sorry. I think there was a problem in transmission. I think I'm probably still having the same problem, which is really sad. Let me see if I'm able to continue. All right, I apologize. That was a break in transmission, but I'm back. Okay, so we're trying to remember how to use a unit circle to find this. We know from idea of the unit circle that, of course, cosine is positive here. So let me see, I'm trying to find my drawer. Cosine is positive here and here, but W must be in 0 and pi. So that cancels this out. So whatever we're looking for is in the first quadrant. And of course, that would be pi over 3. Okay. All right. So now let's move on to how we can find using what is it called again? How we can find using our Pythagoras, or I didn't really cover the part that has to do with calculator because technically we're not supposed to use a calculator with your exams or use a calculator in anything. So I would avoid questions that have you use a calculator. And you would also not have questions like that on the exam. But right now we're going to be looking at how to, given the sides of a right angle triangle, how we can find the answers, the angle of the inverse function. So this little how-to gives us, a right angle triangle that looks like this. We're trying to find theta. Now, if you're given hypotenuse and you're given adjacent, remember your soul? Okay, where this is opposite over hypotenuse, this is for sine, adjacent over hypotenuse for cosine, opposite over adjacent for tangent. So if you're given a side that is hypotenuse and adjacent, you know you're to use cosine. Hypotenuse and opposite, you're to use sine. And if you have adjacent and opposite, you know to use tangent. Okay, so let's take an example. Here we have a triangle and we're trying to find the angle theta. Okay, and in a regular like good old function, we know, so we have opposite and we have So we have opposite and we have hypotenuse, and that gives us sine of theta, and that is 6 out of 10. So this tells us that theta is sine inverse of 6 out of 10. This is not one of our special angles. So, and again, you're not going to be using a calculator in this in your exams, apart from like the regular good old calculator, and it's not scientific. So no one would be asking you to find this. I would not be asking you to find this. Okay. But it's just, you see a triangle, you're given two sides and you're trying to find an angle. This is how you want to go about it. Okay. So next, let's move on to finding exact values of composite functions. So composite functions, I don't know if you remember composition of functions. This can go away. Let's see. No. So if you remember composition of functions, we talked about this a while ago. And this is where you have a function of a function. So you have an f of g of x. Okay. So we can do the same thing with inverse function and trig functions. And of course, from your inverse function section, we had something where we talked about this of x is equal to x. This is not always true for trigonometric functions and their inverses. So say, for example, sine and sine inverse. Sine of sine inverse is equal to x if and only if x is in this interval. So again, this page is very, very important. These intervals are very, very important for you to remember. And they're not really hard to put in your mind. You just have to remember the range and domain for the inverse functions and for the also sine functions as well. Now, given an expression of the form f inverse f of theta, where f of theta is sine, cosine, or tangent, you can evaluate for theta by first checking if theta is in the restricted domain of f, then this happens. So restricted domain are all of these people. Okay, this are the restricted domains that we're talking about. This has to happen. Okay, and if not, you have to find an angle which is within the restricted domain, and you can do that by reference angles. You know, sometimes you subtract 2 pi, or sometimes you subtract 360, sometimes you add 360, all of those kind of things. So now first, let's look at an example that says find the values of sine inverse sine of 5 theta over 6. Okay. Now 5 theta over 6 is, let's see, that would be in the second quadrant. So again, you always, so start, let me put it, so start from the inside. So the same way we dealt with composition functions, you can go back to look at those lessons when you can on composition functions. Okay, you can go back to look at, you always start from the inside functions. So, and in this case, it is sine of 5 theta over 6. Now, if we look at our unit circle, sine of 5 theta over 6 would be 1/2. And why? That's because 5 theta over 6 is in the second quadrant. And in the second quadrant, sine is positive. You can do the whole, and that would be, you can do the whole reference angle thing to again, but yeah, that is, if you look at your unit circle, that's where that's come from. So now what we're left with is sine, I definitely want to change pen here. So we're left with sine inverse of sine 5 pi over 6 is equal to sine inverse of 1/2. And now this brings us to the problem that we've been solving since the beginning, which is we need, we can say x such that sine of x is 1/2. Remember how we've been solving inverse trig problems from the beginning? That's how you want to come back and do this. So you need x such that sine of x is 1/2. But again, x has to be within -π/2 and π/2 because this is the restricted domain for the inverse function, okay? And so, of course, in this case, the best person to be that person is x equal π/6, because that sine π/6 is 1/2. So now, finally, the final answer for this would be 1/2. Oh, not 1/2. We need angle, and that would be π/6. Okay. All right. Next, let's move on to this. This one says find the tan inverse of tan 11π/9. Okay. Again, you want to start by dealing with the inner. So you deal with the inner 11π/9. We can do this in probably 2 ways. Remember, so let me just change pen here. Remember, tan is a periodic function, of period pi. So what this means is f of x plus pi, not f actually in this case, tangent, because that's, so tan of x plus pi is equal to tan of x. And so if I use that, I can say that tan of 11π/9, which is equal to tan of 2 pi. So this is 2π/9 plus pi is equal to tan of 2π/9. Okay, so I have used the periodic function notion to reduce tangent, to reduce our angle. Again, if you're given any angle, so 11π/9 is a little bit in the third quadrant, so that'll be in somewhere here. We know in there that tan is positive, so that's good. And so see. Again, remember that tan inverse or tan inverse tan is equal to x only if x is between -π/2 and π/2. What have we found? We have found 2π/9. So the question now is this within -π/2, π/2? Okay. 2π/9 is definitely in the first quadrant. I don't know why this happened, but 2 pi, I'm having connectivity issues today. 2π/9 is definitely in the first quadrant, and so most of all, you can always check. You can always check who is bigger. So 2π/9, π/2. I want to check who is bigger. You check the LCM. That's 18, and this gives you 4 pi. This gives you 9 pi, so this is bigger. And so 2π/9 is less than π/2, and so it is in the interval -π/2. So in this case, we have that tan inverse tan of 11π/9, which again we found to be equal to tan inverse tan of 2π/9 is equal to 2π/9. That was because 2π/9 was in our restricted interval -π/2 to π/2. Okay. All right. Next, let's look at, so what we just looked at different examples that had to do with sine inverse sine, tan inverse tan, but what if you had a question that was asking you to do tan inverse cosine or sine inverse tangent or any of that sort? Now, this is how you want to go about it. Okay. If you have functions of this form, so I don't know, or this form, we evaluate them by first checking, is x in the 0 pi? Then you do this. And this pi over 2 business minus x is coming from the fact that if you look at a right angle triangle, you have this, so A is opposite, B is adjacent, C is hypotenuse, but the angles in the triangle sum up to 180 degrees. So this is already 90 degrees or pi over 2. And so if this is pi, then this is pi over 2 minus pi. Okay, so if x or pi, whatever it is you're trying to look for, is in the interval 0 pi, then the sine inverse of cosine is pi over 2 minus x. If it's not, you have to find another. Anyways, let's take an example. Let's take an example, because with these things you just keep going round and round. But a very good thing to note here is when you're given a problem like this, the knowledge that you've gained from 6.2 will help you in the sense that you want to first, so let's draw a line here to separate our problems. You want to first draw a right angle triangle. Mine is not drawn to scale. And again, start with the inner. So tan inverse of 5 over 12, right? If this is equal to, say, x, then tan of x is 5 half. We talked about this in the second slide. And I can use this information given to me here to create my right angle triangle. So if this is my right angle triangle, and I call this angle x, tan is opposite over adjacent, so opposite 5, adjacent 12. Again, pardon me, I'm not drawing any of this to scale. I just need to get the point across. And we can use our Pythagoras identity, which is opposite squared plus adjacent squared is hypotenuse squared. So this is 5 squared plus 12 squared, which I'm just going to tell you is 13 squared. Because 5 squared is 25, 12 squared is 144. If you add that, that's 169, and that is 13 squared. Okay, so what have we found from this? I said if tan inverse, okay, so see how I set up the problem. I said tan inverse, I said let it be the angle x. And I used x, and I used the idea that tan of x is 512. I use it to find, so now this is what my right angle triangle looks like. I'm definitely not good at this drawings, but just pardon me. So this is 5, this is 12, this is x, and this is 13. So I've used the inner information to draw this right angle triangle, and I have all 3 sides. So if I'm looking for cosine of tan inverse of 5/12, which I said let this be x, cosine x. Then I come to my right angle triangle. Cosine is adjacent 12 over hypotenuse 13 and 12 over 13. So this is how you can use your right angle triangle to simplify those problems for you. Okay. Next, let's look at this problem here. Again, you want to start with the inner. And if I'm starting with the inner and I say, let sine of 7/9 be r, then sine of r is 7/9. And I can use this information to draw a right angle triangle. I'm going to start changing pen here. I don't like this yellow anymore. So if I have this, and I call this r, sine is opposite over hypotenuse. So this is 7, this is 9. I can find this using the Pythagorean identity. If I call this a, then I know that 9 squared is 7 squared plus a squared. And this is 81, this is 49 plus a squared. Okay, so a squared is 81 minus 49. And that is equal to, that's a 2, 6, 22. No, 32. Okay, so a is root of 32, plus or minus, but we're dealing with lines, so it's a positive square root, and that is 4 root 2. Okay, so this is 4 root of 2. So again, sine of r was 7 nines. And so cosine of sine inverse of 7 nines, which I have called cosine of r, from my right angle triangle, cosine is adjacent 4 root 2 over hypotenuse 9. And that is it. We are done. That's the evaluation, and that's the final answer. Okay, please look out for the assignments posted, and please let us know if you have any questions. You have a great day. Thank you.